So one of the very nice things about working in the UK space industry is that we're trying to do some really interesting things, and here to talk to us about one of the very interesting things that the UK is involved in at the moment is Abbie Hutty, who's going to talk about going to Mars. Thank you, Abbie.
Hi, so mic's working, good start. I work for Airbus, as we've heard a few of the people do today, and at the moment I'm the lead structures engineer on ExoMars, which is the first European Mars rover mission. But I'm going to talk more generally about Mars, how we get there, what we have to think about, and why we might want to go there. So, first of all, we would like to put a rover on Mars. Sounds like a simple enough proposition. But how big is Mars? Where is Mars? What is going on with Mars? We've heard a bit about the planets today. We've heard about satellites. How do we put this into perspective? So I'm going to need 4 volunteers for this. I'm going to go with the conventional 12 years and under. I think that was what we were defining before. 12 years and under, 4 volunteers. I've got one hand here. Very excited about this one. This one in a blue jumper. I've got... Who have I got? Oh, I've got one in a spotty top up here. It's a bit dark. I can't see darker colours, so you're definitely in luck if you're wearing a light colour. And I think I can see a waving orange jumper. Is that orange? We like orange, so you're in favour. Okay, so my 4 volunteers. Welcome, welcome. Who would like to be the Earth? That was quite immediate. Okay, we've got the Earth, the Moon, Mars and a satellite. So we've got left Mars, the Moon and a satellite. Who would like to be a satellite? Ooh, that hand was first, okay. So then we've got a Moon and Mars. Who wants to be the Moon?
I'll be the Moon.
And are you happy being Mars? Excellent. Okay, so drawing on standard sports equipment, we're going to call the Earth a football because everyone knows how big a football is. So we've heard earlier that Mars is smaller than the Earth. That was in our higher-lower quiz. So I have this particularly non-standard sports ball size. It's really hard to find a 12-centimetre ball, just throwing that out there. So who's going to be Mars? Mars. That's Mars. And then we've got the Moon. Now, this is a tiny bit small for the Moon, but it is not a million miles away. So we've got the Moon here. And our satellite, I'm going to take this speck of dust. There you are, this is your satellite. Okay, so this is how big our things are relative to each other, but how far away are they? So this is the Earth. We know where the Earth is, we're all standing on it. This is our Moon, which is a golf ball. This is Mars, which is a little minion ball, and we can't really see the satellite. That's fine. No offence, it's still a really important job. Okay, so I started drawing this out. So we know that the distances we're talking about are huge. So I've drawn the Earth quite small. I think you'll agree, quite small. So first of all, what's the closest thing to the Earth out of the things that we have here? Is it satellite, Moon, or Mars? Satellite? Okay, so I would like the Earth to stand here. I would like Mr. Satellite to come and stand pretty close. And we need the satellite to be about 50 centimetres away from the ball. So he's going to go around about here, 50 centimetres from the centre of the ball, so about here. Okay, good. So that's how far our satellite is away, but of course we can't really see it. We can't draw it to scale on that map. Okay, brilliant. So next is the Moon. The Moon, where are we going to put the Moon? Start standing here and let's ask the people. Ask the people. Come on, people. Does she need to be closer or further away? Okay, so I started drawing the line of how far it needed to be on that scale, and no, it needs to go far, far further away than that. Okay, so we'll draw the Earth a little bit smaller. Okay, that's half the size. So this is our satellite. And the moon is about 5 meters away, so right the other side over here. This is our moon to scale. Okay? So if you imagine this is the Earth, everyone that you love is on this pale red dot. And this is to scale, roughly, how far away the moon is. Okay? So, Mars, how far away do you think you're going to have to go? Way, way off the side of this screen. Okay, let's draw the Earth even smaller. Okay, this is the Earth. You can barely see it. There's the moon. I haven't even bothered with the satellite because that's so tiny that it's not even worth talking about. Where is Mars? No, it needs to go far, far further away than that. Actually, you're going to have to go to Hyde Park and stand in the middle of the Serpentine. And then that's about the closest you will ever get to the Earth. So if you imagine, this is to scale. I'm not going to make you go and stand in the middle of the Serpentine. If you imagine this is the scale, hold it up so that everyone can see how big Mars is. Real scale. Let's put the sun somewhere where we know everyone's heard of the London Eye, right? So the London Eye is where the sun is, actually maybe just a bit behind it. In the park, because otherwise you might kind of freak out the people on the London Eye. And that puts the Earth right in the middle of us here in the Royal Institution. That's a really good scale. We like that. To scale with footballs and golf balls and other things like that, that puts Mars, oh, no, that's the Earth's orbit, that puts Mars about in Selfridges, having a little Saturday shop, and it will go around right the way out to Tower Bridge. Would you like to go to Tower Bridge? Not right now, maybe later. Out round Vauxhall and all the way around like this. You'll see that the orbits aren't quite circular, they're slightly elliptical, so it does wobble around all over the place. So if you imagine that we're standing on this football, that's occasionally going through here in the Royal Institution, and we have to hit this Minions ball, standard sporting equipment and all that. This is to scale what you're going to be aiming at. So you're aiming at a Minions ball that's whizzing around, going through Tower Bridge, out to Acton, down nearly to Clapham. This is the scale we're talking about. It's pretty hard to aim in the right direction. Can you imagine a sharp shooter standing on this football that's whizzing around London, trying to hit this ball out in Vauxhall or over by Tower Bridge or something like that? This is what we're trying to do with our Mars mission. Thanks, guys. You can put the balls somewhere down here. Well volunteered, and thanks for not going out to stand in the middle of the Serpentine, because that probably we don't have the health and safety risk assessment for that right now. So why Mars? Why do we want to go to Mars? Well, really, because we screwed up a couple of hundred years ago is why I want to go to Mars. So a couple of hundred years ago, we first got mainstream telescopes to a fairly decent standard. And there were lots of astronomers looking at the night sky and seeing the planets with their own eyes for the first time. And one of those astronomers was an Italian called Schiaparelli, or probably a very different pronunciation of that because he was Italian and I can't do that with my throat. And Schiaparelli looked at Mars and he could see these dark lines across the surface of the planet. And he wrote about this in a journal and described them as canali, which in Italian means channel. It can be kind of man-made, or it can be a gully or a ditch or a riverbed or anything like that. Canali. And then an American astronomer read this, being renowned for languages as they are. He read the word canali and thought, oh, canals, like we have here on Earth to transport water and equipment and bits and pieces around the planet. And he imagined these Martians building these canals to take liquid water from the polar ice caps to what we could see was quite a kind of orange, dusty, deserty looking equatorial region around the planet. And he was so inspired by this idea that he started mapping the canals on Mars. He made it his life's work to map the canals on Mars. Now, any of you that has looked through a telescope will know that because you've got a light source shining and reflecting between lenses and things, quite often you get an effect, which is that you can see the blood vessels in the back of your eyeball. And actually, this is what Percival Lowell was looking at, and this is what he made it his life's work to map. So it wasn't quite as exciting as he imagined it was, what he was doing, but we do have some very good maps of the back of Percival Lowell's eyeballs. But ever since then, we've had a little bit of a fascination with Mars. We've had so much sci-fi written about Mars and these Martians and Martian canals and all of these things that Martians are meant to be doing. It's our closest neighbour. It's the most similar planet in the solar system to Earth, both in terms of geography, in geology, and all kinds of other things as well. It's even got a 24-ish hour day. So we're fascinated by Mars. We've always wanted to go there. We've always imagined what it would be like to meet the Martians. And so we've spent an awful lot of time and energy trying to do just that. You won't be able to see all of the titles on here, but this is all of the missions that we as humanity have ever sent, either directly to Mars or with a science mission involving Mars at some point in their overall mission. And you'll notice that some of them have little explosion marks at the end of the lines. Now, pro tip, that's not a good thing. So you'll notice if you actually count them up, we're very, very nearly 50-50 on all of the missions that have been intended to take some readings or to go to Mars, failing and actually succeeding in that scientific mission. But we have sent loads of missions before. So what's my mission about? Oh, sorry, wrong bit of the presentation. Carry on. So the first one that we actually had that went past Mars was just a flyby. So Mariner 4 went whizzing past on its way to the outer solar system, and we took 21 black and white photos of Mars as we went shooting past. So we can do flybys. We actually landed on the surface with Viking, and then we took photos of the surface, and we saw that Mars was a dry desert planet, as we'd suspected. We've got things that are actually orbiting Mars. So they've gone to Mars, captured orbit, and now they go around and around the planet taking images of Mars. So this is one of them, Mars Express, built by my company, and these are some of the images that we get back of the surface. We can actually see in 3D because we've got cameras in stereo, two different ones like we have eyes, so you can see depth because of that. And we can take these images using that instrument. We've also taken photos of the moons of Mars. There's two, Phobos and Deimos. This is one of those moons. When it got close enough to the orbiter that we could see it. So we've got orbiters, and then we've got rovers. And I think we can all agree that rovers are the coolest, aren't they? We like rovers. We want to leave tracks on the surface of the planet. That's where it's at, isn't it? That's the coolest thing. We want to look up from our rover and see the Earth as a tiny speck in the sky. That's the coolest thing, isn't it? We like rovers. Okay, so we want to build a Mars rover. What do we have to think about? Well, for a start, Mars is really cold, like really cold. So in winter, at the poles, it can get down to minus 130 degrees centigrade on Mars. That's pretty brisk. Even by day, at the equator in the summer, you're very rarely going to break through 0 degrees. You might get up to 5 or 10 degrees on a really hot summer day. There's a lot of radiation there. We've heard humans, if they were there, would have to live in a hole because there's so much cosmic radiation hitting the surface. You're not really protected by the atmosphere that we have here on Earth. You're also not protected by the geomagnetic field that we have around the Earth that creates all of the radiation bands that help to shield us from that stuff coming from space, and various other things as well. So this is the temperature on an average day on Mars. It's pretty chilly. Continues getting chilly. This is midnight, all the way through to daytime and then out again. I've put the red lines mark where standard commercial electronics work. So clearly that's a challenge. We've got dust. So taken from the Hubble Space Telescope. This is a standard picture of Mars. And then a few months later, in the same year, this happens. This is a global dust storm. Just like you get dust storms here on Earth in deserts, from the day to night temperature, changing the temperature of the air above the desert surface and lifting dust up into the atmosphere. On Mars, there's such fine dust, it's so dry, and there's not as much gravity and things like that to drag it back down again. So actually these can all coalesce and create these global dust storms. And then those collect on the surfaces of your solar arrays. So this is Spirit taking a selfie before they were cool, showing all of the dust collecting on the surface of the solar arrays. But actually, if you've seen The Martian, it's not really the wind speeds of the storms and the damaging effects of being pummeled by the dust and the sand that we're worried about. It's more the dust collecting on things, getting in our motors, getting on our solar arrays, collecting on the lenses of our cameras that are the most punishing things for the mission. We also want to look for life on Mars, which, as we've heard before, means that we don't want to take it with us. So we've got to be very careful about how we build our rovers in a very sterile environment and make sure that they're not going to take anything with us that's going to contaminate the readings of what we're looking for. We've got to survive launch. Our personal mission is going on a Proton rocket from Russia. And we've got to get there. So it takes us 6 to 9 months, depending on when we launch, to get across to Mars. You have a good opportunity every 26 months when the planets align and they're at their closest. So if you hop across then, you can get across in 6 to 9 months. We've got to survive landing on the surface. So various different stages of getting down. We've seen the sky crane with Curiosity. We've got a very similar approach with our mission. And then we've got to know why we're going there in the first place. With ExoMars, we're looking for life. We want to answer that question of, are we alone in the universe? The reasons that we're interested are because on Mars, we know that there's methane, which here on Earth normally comes from either volcanism or from biological processes. And we know there's no active volcanism on Mars, but there is active methane release. So that could be an indicator for life. And we also know there's a lot of water there, not just at the poles, but actually all around the surface. Curiosity found 2% by weight of the soil, even just at the very surface of Mars, is water, which is a really good indicator that, A, as human beings, we could go there and harvest enough water to survive, but also if there was a life that was dependent on water, it would be able to find it across the planet, wherever it was. So we need to pick a landing site. That has to be, if you're using solar panels around the equator, at least enough that you get enough sunlight. But also on Mars, quite interestingly, it has to be low in elevation enough that you can use a parachute to land, because you have these very high lands at the bottom of the planet. We think that there used to be an ocean across the North Pole. So actually, all of the yellow area here is too high. There's not enough atmosphere between you entering it and you hitting the ground for you to slow down using parachutes. So you can only land in the kind of turquoise areas. So this is where it's at, this area over here. So these are the different landing sites that we're considering for our ExoMars mission. It's also clearly the coolest place to go, because in The Martian, this is where Mark Watney goes. He lands here, goes down to Pathfinder, back up again, and then over to Schiaparelli crater. Remember Schiaparelli, that Italian dude? Yeah, he gets everywhere on Mars. Then you need a team. This is Christmas jumper day at Airbus. Particularly like this guy's suit. He's looking rather fine. You need to design a rover. Yeah, straightforward. You need to be able to pack it down so that it doesn't get damaged on the way. So fold everything up nice and compact to go on the rocket so it doesn't shake itself apart. And then you have to decide what to take with you to actually take those interesting readings on the surface. Pro tip, take a drill if you're looking for life, because nothing will survive at the surface. And then there's all this other stuff that you also have to think about. That's how you make a mission to Mars.
Thank you. Being careful not to kick Mars out of the way as I get down. Any questions for Abbie?
Presumably another thing you have to survive is politics. If you're on a Russian launch next year, you have to hope things don't go pear-shaped.
Yep.
Just saying.
Yep.
I have a question. Are we going to ever put a microphone on Mars? I've never, for all the we've done, no one's ever heard of Mars.
You've been talking to Jeremy, haven't you?
No, I haven't actually. Well, I haven't, well, not about that.
Our PR director at Airbus really wants us to put a microphone on the rover just so that we can hear what it sounds like on Mars, which is a great idea, but basically it's not going to sound of anything because there's not enough atmosphere there to really transmit sound. So you might be able to get a very, very, very sensitive microphone that might be able to hear stuff that the human ear wouldn't hear, but beyond that, no, not going to hear an awful lot.
Just a quick question. So we know microbes can survive rather well in difficult environments.
Uh-huh.
I can see the work that has to be done here to stop any contamination. But what got done for Viking and the earlier probes? And who's to say it's not all over the place now?
Actually, Viking was very good with their planetary protection because all of the countries got together. I think there's 127 countries currently signed up to the International Space Treaty. And we all agreed that, oops, we kind of screwed up with the moon. There's stuff all over the moon. We probably shouldn't do that again. So we made this treaty that said that we're not going to contaminate the other planets. And the first missions to land on the surface of Mars didn't know if we were going to find actual sort of full humanoid life forms running on the surface. So we needed to be absolutely sterile so that we didn't give them the plague or something and they all dropped down dead and started an interplanetary war. So they were all highly, highly sterilised. It helped that they were basically 70s technology. So they were quite easy to sterilise by comparison to what we have today. The kind of batteries and PCBs and all of that kind of stuff were somewhat sturdier, more robust, more clunky, and therefore easier to sterilise. Unfortunately, with Viking, we saw that there wasn't any things running around on the surface. There weren't great cities or roads or infrastructures there. So after that, we kind of declassified Mars to a less extreme level of planetary protection requirement. And only with our later missions, when we've actually found that actually there is water, there is methane, there might even be liquid water on Mars, we've actually ramped it back up again. But we've had a certain level of contamination requirement all the way through, and hopefully any contamination that would be in a fairly discrete area around the rover and would be being bombarded with radiation and stuff on a regular basis, so it's being killed, hopefully as fast as it's likely to be reproducing.
I'm just curious to know, if you missed that, you were talking about the window to launch between the Earth and Mars.
Mm-hmm.
If that window was missed, how long will the mission to Mars take?
Years. You're talking about 50 million kilometres at its closest pass, but it's, 230 million kilometres away from the Sun. So at its worst case, we're 150 million kilometres from the Sun, it's 230 million kilometres in the opposite direction. So that's really quite a long way by comparison to the 50 million kilometres that you can hop across. Just simply hop across when it does come whizzing past. So it's much quicker to wait for it to come past and then hop across rather than to launch and try and go right the way across the solar system.
I'm aware there's a lot of people that would quite like to ask questions, but I think in order to keep reasonably to the schedule, we're going to have to move on now. So perhaps if I can ask you to catch Abbie at the break.